Welcome back to a new machine learning tutorial. In this video, we are going to talk about support vector machines classifier. We are going to talk about the logic behind the algorithm. We are going to look at how we can code it using Python scikit-learn. And lastly, we are going to talk about how we can do hyperparameter tuning. Let's start coding. I'm in my code editor right now. You can use any code editor that you want. I'm going to be closing this welcome page and I'm going to create something like support vector machines.ipynb, and let's talk about it after selecting the kernel and creating a title like support vector machines. So it's a powerful supervised machine learning algorithm, and the core concept of support vector machines is to find the optimal hyperplane that best separates data points of different classes in a high dimensional space. The goal is to maximize the margin between the closest points, which we can also refer as support vectors, of the different classes, ensuring a clear boundary with the least error. So in this tutorial, I'm going to be talking about the logic or math behind the support vector machines. Then I'm going to be training a base model support vector machines classifier. Then I will be talking about the parameters it can take, and then I will show you how you can do hyperparameter tuning for getting the optimized performance from the model. So let's talk about the logic behind that, and let's firstly talk about the hyperplane. A hyperplane in an n-dimensional space is a flat affine subspace of dimension n-1. For example, in a two-dimensional space, the hyperplane is a line, and in a three-dimensional space, the hyperplane is a plane. And the equation of the hyperplane can be written as w multiplied by x plus b equals to 0, where w, this one, is the weight vector normal to the hyperplane, x is the feature vector, which is going to be our input data that we are passing into the model, and b is the bias term. So let's talk about the margin. Margin is the distance between the hyperplane and closest data points from either class. So let's say like margin is the distance between the hyperplane and the closest data points from either class, which also known as support vectors. Support vector machines aims to maximize this margin to create the most robust classifier. So let's start the coding. What I'm going to do at the first place is I'm going to be creating a data set to work with. So I will say from scikit-learn that datasets import make classification. And then I'm going to say x and y. I will use make classification. I will say number of samples is going to be 1000, and number of features is going to be 2. Number of informative is going to be 2. Number of redundant is going to be 0. And number of clusters per class is going to be 1, and number of classes is going to be 2, which is going to lead to a binary classification problem. By the way, it's defaultly 2, 2. So I'm going to call the x matrix firstly for showing you, and we have two features. As you can see, we have a matrix like this and y vector. Here is our y vector. Again, we have a binary classification problem which we need to predict 1 or 0 with the machine learning models. So let's quickly visualize this information. I will say import matplotlib.pyplot as plt, and then I will say plt.scatter. I'm doing that quickly for showing you the data we have right now. X, and I will say 0 like this, then I will say x, and this time I will say 1 for the other feature. C is going to be equal to the y, and color map, let's say winter. And we can give it an x label like feature 1 and y label like feature 2, and we will use plt.show, and here is our data. So by the way, since we are not specifying any kind of random state in here, when we make this run again and plot it, we are going to have a completely different data set, and we can play with them as we wish. Like I'm going to stop on something that I think it's going to be good for this tutorial. Yeah, this one's great. So we can work with this. In the next step, what we are going to do is we are going to do train test split. But firstly, let's do our imports. From scikit-learn.supportVectorMachines, import support vector classifier. From scikit-learn.model-selection, import train test split. And from scikit-learn.matrix, import accuracy score. Then after this import, we are going to be using train test split for splitting our data. I will say xtrain. I have a tutorial on this concept, train test split, but I'm going to talk about it quickly for summarizing the information. But if you want to learn more about this, you can watch the tutorial. It's on my machine learning playlist where I have more than 30 videos, 30 machine learning tutorials just like this one. So in here, what I do is I'm splitting up my data as xtrain, xtest, ytrain, ytest. Xtrain and ytrain are my training set, xtest and ytest is my testing set. And by specifying the test size 0.3, I have 30% of the data in the testing set and 70% in the training set. So in our case, we have 1000 samples, so 700 data points are going to be in the training, 300 is going to be in the testing. And we are going to train our model with xtrain and ytrain. Then we are going to use our model for making predictions using xtest, and we are going to compare the performance of our model on the y-test. So let's train the base model without any type of parameter tuning. And by parameter tuning, I'm meaning that in most of the machine learning models, we have parameters that we can optimize and change. So I will show you how you can optimize the performance. So I will say support vector machines model is going to be support vector classifier. Then I'm going to train my model using fit method like this. And we can make predictions using this model like predict, xtest, and here they are going to be our predictions. And I'm going to be storing them in something like, let's say y predictions, and I will say svm model.predict xtest. Now I will get the accuracy score on that, calling it like y-test and y predictions. So here is our accuracy score. So this is a really good accuracy score, 0.99. But what I'm going to do is I'm going to create a new data set and train the model again. So I don't want that high accuracy score on the base model side. And this is going to be an easier one too. We can do like, let me change this to, I think this one is better. So I'm going to make them all run again. I will say this, and I'm going to take the predictions and accuracy score. Now it's 0.88. Okay, so let's talk about the parameters we can tune. So I'm going to be firstly starting with the C, which is regularization parameter. And this controls the trade-off between achieving a low training error and a low testing error. A smaller value of C creates a wider margin at the cost of more classification errors. And we have the kernel, which determines the method used to transform the data. We have options of linear, polynomial, or radial basis function, which we are going to refer as RBS. And we have gamma parameter. It defines how far the influence of a single training example reaches. Low values mean far, and high values mean close. And we are going to have degree. When we are using the polynomial kernel, this determines the degree of the polynomial. Great, so let's do hyperparameter tuning. And for that, we will say from scikit-learn.model-selection, import grid search cross-validation. And in grid search, we are going to give a parameter grid, and all the combinations of the parameters are going to be tried out, and it's going to return us the best performing one. So I'm going to define the parameter grid, and I will say like it's going to be a dictionary. Let's start with C. Actually, let's go with this order. So I will say C. It can take values 0.1, 1, 10, 100, and also let's give 0.01. So it's completely up to you. You can extend this list and try more parameters. More parameters means probably a better model because you're trying more stuff, but it has a more computational cost. So I will say linear, RBF, and polynomial. Then I will say gamma, and it can take values like 1, 0.1, 0.01 and 0.001. I'm not going to extend it more. Degree we can give like 2, 3, 4, which is going to be more than enough in my opinion for this short tutorial. And now I'm going to be creating the grid search object, like on grid search cross-validation, support vector classifier. I'm going to set the parameter grid like this, and then I'm going to give cross-validation as 5. So cross-validation splits the data into 5 folds since we give 5, and trains the model with the 4 folds and tests it with the 1 fold we have for each fold. So after setting this, by the way, I have a tutorial on this cross-validation too. You can check that for understanding the concept better. I will say that fit, and I'm going to be fitting the model with this. Now it can take some time, so I'm not going to be recording all the process. I will record back when this finishes. So it finished quicker than I expected, and we finished the operation in 12 seconds. And now we can see the best parameters we have. So I will say grid search best parameters, and C is 100, degree is 2, gamma is 1, and kernel is the RBF. So how you can extend this parameter grid is, you see C is 100, so you can add 200, 50, 60, 70, 300, 400, like you can extend in the right side. And now we have the gamma of 1. Okay, so now let's make predictions with the tuned model. So for that I will say best model, and it's going to be grid search best estimator, and I will say why prediction tuned is going to be best model dot predict, and we will predict the X test in here, and we can get accuracy score on Y test and Y predictions tuned. So we are going to have 0.99 in here right now. We improved the model performance with hyperparameter tuning. So that's it for our tutorial. Let's summarize what we do. We talked about the support vector machines and how it's working behind. Then we talked about definitions, and then I create the data with make classification. We visualize it, and then we import support vector classifier, train test split, and accuracy score from scikit-learn. Then we apply train test split with the 0.3 test size, and we initialize the base model. We train it, and we make predictions with it in here, then store it, and we got the accuracy score from that. And then we talked about the parameters it can take, like C, kernel, gamma, degree, and we imported grid search, which is used for trying out all the possible combinations of these parameters. And then we find our best parameters after fitting the grid search, and we get the accuracy score from the hyperparameter tuned version 0.99. Thanks for watching this tutorial on support vector machines classifier. I have a playlist named machine learning tutorials where I have more than 40 videos just like this one. You can check the playlist in the description or from the cards of this video. I'm sharing new data science videos every week on my channel. You can subscribe to my channel for more videos like this. Have a great day.